I want to start by telling you plainly what I think this title gets right and what I think it overstates. Because I've spent this entire series trying to give you honest physics rather than either false optimism or manufactured despair, and I don't intend to abandon that approach now, even with a title as provocative as this one. Mars colonization, in the sense that phrase is typically used in public discussion, a self-sufficient, thriving human settlement, growing and expanding independently of Earth, the way the word colonization implies when applied to historical settlements on our own planet, is not currently supported by the physics, chemistry, and biology we understand. I don't think that makes it a permanent lie in the sense of something intentionally deceptive. But I do think the gap between the rhetoric surrounding Mars colonization and the actual physical requirements for sustaining human life there, independently of continuous resupply from Earth, is far larger than most public discussion acknowledges. And I want to walk you through exactly why. Let me begin with radiation, because I think it represents the single most under-discussed barrier to genuine long-term Mars settlement, more fundamental even than the propulsion and return journey problems I've already covered in an earlier conversation. Earth's surface is protected from the most dangerous forms of space radiation by two overlapping shields, both of which Mars almost entirely lacks. The first is Earth's magnetic field, generated by the churning motion of molten iron in our planet's outer core, which deflects the vast majority of charged particles arriving from the sun and from deep space, funneling them harmlessly toward the poles rather than allowing them to reach the surface where we live. The second is Earth's thick atmosphere, providing the equivalent of roughly 10 meters of water shielding against the radiation that does make it past the magnetic field, absorbing and scattering high-energy particles before they can reach ground level in dangerous quantities. Mars has neither of these protections in any meaningful sense. Its core solidified, or at least its dynamo effect ceased, billions of years ago, leaving Mars with only weak, localized patches of remnant magnetism in certain regions of its crust, nothing resembling the global protective field Earth generates. And Mars's atmosphere, while real, is extraordinarily thin, roughly 0.6% the surface pressure of Earth's atmosphere, providing shielding equivalent to only about 16 grams per square centimeter, compared to Earth's roughly 1,000 grams per square centimeter. This means the Martian surface receives a radiation dose from galactic cosmic rays and solar particle events dramatically higher than anywhere on Earth's surface, including levels considerably higher than what astronauts experience aboard the International Space Station, which at least benefits from the partial protection of still being within Earth's magnetosphere. Measurements taken by the Radiation Assessment Detector aboard NASA's Curiosity rover, operating on the Martian surface continuously since 2012, have provided real, measured data on this exposure rather than theoretical estimates alone. The instrument recorded an average surface radiation dose equivalent to roughly 0.64 millisieverts per day under normal conditions, which extrapolates to somewhere around 233 millisieverts per year of continuous surface exposure. For comparison, this is many times higher than the roughly 1 to 3 millisieverts per year most people receive from natural background radiation here on Earth, and it approaches, over a period of just a few years, the career radiation exposure limits that space agencies currently set for astronauts, specifically because of the elevated lifetime cancer risk this level of cumulative exposure carries. I want to be precise about what this means for the specific idea of colonization as opposed to shorter duration exploration missions. A crew spending a year or two on the Martian surface, protected by whatever shielding their habitat provides, faces a serious but arguably manageable radiation risk, comparable in some respects to other elevated risk occupations, and one that mission planners can account for through careful habitat design, limiting surface time outside protective structures, and accepting a certain increased lifetime cancer risk as a known cost of the mission, the way test pilots and other high-risk professionals have historically accepted comparable trade-offs. But colonization, in any meaningful sense of that word, implies not a temporary mission, but permanent or multi-generational habitation, potentially including families raising children on the Martian surface across years or decades. And here the radiation problem becomes categorically more serious because the elevated cancer risk from cumulative radiation exposure would apply not just to a small number of highly trained, carefully selected astronauts accepting a known occupational risk, but to an entire population, including children, whose developing bodies are generally understood to be more vulnerable to radiation-induced cellular damage than fully mature adults, and whose entire lives, rather than a limited mission duration, would be shaped by essentially permanent exposure to environmental radiation, many times higher than anywhere permitted on Earth. The proposed solutions to this problem exist, and I don't want to suggest they're purely theoretical, but I do want to be honest about their scale and cost. Serious habitat designs for long-duration Mars settlement generally propose either burying structures under several meters of Martian regolith, using the soil itself as radiation shielding in a manner analogous to how Earth's atmosphere functions, or constructing habitats within natural formations like lava tubes. Geological features believed to exist on Mars, similar to those found on Earth and the Moon, which would provide substantial rock overburden as natural shielding without requiring extensive excavation. Both approaches are physically sound and represent serious, legitimate engineering proposals. But both also mean that genuine, permanent Mars settlement, unlike the romantic imagery often associated with the word colonization, would likely require inhabitants to live almost entirely underground or within heavily shielded structures, with only limited, carefully managed excursions to the actual Martian surface, a considerably less appealing prospect than the sunlit, domed cities of popular imagination, and one that raises serious, largely unaddressed questions about the psychological and social effects of multi-generational life lived predominantly in enclosed, subterranean, or heavily shielded environments. I want to turn now to a second, equally fundamental problem, the question of what a genuinely self-sufficient Mars settlement would actually need to produce for itself, rather than continuing to depend on resupply from Earth, and why that self-sufficiency threshold sits so much further away than most popular discussions of Mars colonization acknowledge. The core physical requirement for any settlement claiming genuine independence from Earth is what's sometimes called a closed-loop life support system, one capable of recycling air, water, and, most challengingly, food indefinitely without requiring continuous imports of raw materials or replacement components from Earth. I want to walk through exactly how far current technology sits from achieving this, because I think the gap is considerably larger than public discussion typically conveys. Air and water recycling have been demonstrated with reasonably high efficiency aboard the International Space Station, whose life support systems recover roughly 90 to 98% of water from crew respiration, sweat, and even reclaimed urine, and generate oxygen through electrolysis of that recycled water. This represents genuine, impressive engineering, but even this well-developed system still requires periodic resupply of replacement filters, chemicals, and components from Earth, and still operates at a scale supporting only a handful of crew members rather than a genuine, growing settlement population. Scaling this technology to reliably support dozens, hundreds, or eventually thousands of people for years or decades, with failure rates low enough that a malfunction doesn't become a life-threatening emergency, given the complete absence of rapid resupply capability from Earth, represents an engineering challenge that has never been attempted at anything resembling the required scale. Food production presents an even more serious, unsolved problem. Every serious proposal for Mars settlement self-sufficiency depends on some form of closed-loop agriculture, growing food crops within controlled environment structures using Martian regolith, processed to remove or neutralize the perchlorate compounds that make raw Martian soil toxic to most Earth plant life, combined with artificial or filtered natural lighting, carefully managed atmospheric composition, and recycled water and nutrients. Experiments conducted on Earth, simulating Martian regolith composition, have demonstrated that certain crops can indeed grow in processed Martian analog soil, which represents encouraging genuine progress. But growing individual test crops in small, carefully controlled experimental plots on Earth is a categorically different challenge from producing the full, nutritionally complete, calorically sufficient diet an entire settlement population would need year-round, using only Martian resources, artificial lighting powered by a Martian energy infrastructure, and a closed nutrient cycle that doesn't slowly deplete or become contaminated over years of continuous operation, a level of agricultural self-sufficiency that has never been demonstrated even in Earth-based closed ecological system experiments, several of which, including the well-documented Biosphere 2 project conducted in Arizona during the early 1990s, encountered serious, difficult-to-predict problems with oxygen depletion, unexpected pest population explosions, and nutrient cycle imbalances, despite operating under far more favorable conditions than an actual Martian settlement would face, including the ability for researchers to intervene in emergencies without a multi-month communication delay and no possibility of physical resupply. I want to address energy production directly because I think it represents a frequently underestimated bottleneck sitting underneath every other self-sufficiency requirement I've described. Mars receives considerably less solar energy than Earth, roughly 43% as much, due to its greater distance from the Sun. And that reduced solar input is further diminished by regular, sometimes severe dust storms, including planet-encircling storms that have, during robotic missions, reduced solar panel output so severely that missions dependent entirely on solar power have been forced into extended low-power survival modes, and, in at least one case, permanently ended a mission's operational life when dust accumulation and reduced sunlight combined to prevent the spacecraft's batteries from maintaining sufficient charge. A genuine, growing Mars settlement, requiring substantial and reliable energy for life support, agriculture, manufacturing, and eventually industrial-scale activities like the in-situ propellant production I discussed in our conversation about Mars return journeys, would need an energy infrastructure considerably more robust and weather-resilient than solar power alone can currently provide, pointing most mission architects toward nuclear power, specifically small, modular fission reactors, as the most plausible primary energy source for genuine Mars self-sufficiency, technology that NASA and other agencies have real ongoing development programs for, but that has never actually been deployed and operated for years at a time on another planetary surface. I want to bring these threads together and address the core claim in this title directly. Is Mars colonization, as the concept is typically presented in public discussion, actually supported by the physics we currently understand? I think the honest answer requires distinguishing carefully between several different things that often get conflated under the single word colonization. Establishing a small, temporary research outpost on Mars, supported by continuous resupply and technical support from Earth, similar in concept to Antarctic research stations here on Earth, is well within the reach of physics and engineering we largely understand, even if significant technical challenges, particularly around the return journey I discussed previously, remain unsolved at the required scale. This is achievable, and I don't think honest physics forbids it. But genuine colonization, in the sense the word implies when people discuss Mars as humanity's backup planet, or as a location for a self-sufficient, independently thriving civilization capable of surviving and growing without continuous support from Earth, requires solving an entirely different, dramatically more demanding tier of problems simultaneously. Radiation shielding sufficient for safe multi-generational habitation, closed-loop life support operating reliably at a scale and duration never before demonstrated, closed-loop agriculture capable of full nutritional self-sufficiency using Martian resources, and an energy infrastructure robust enough to support all of this reliably, despite Mars's reduced solar input and severe dust storm risk. None of these individual problems violates any law of physics I'm aware of, but the honest current state of the relevant technology sits, in nearly every case, many years or decades of dedicated research and full-scale testing away from being demonstrated as reliable enough to support human life, particularly the lives of children and multiple generations, independently of Earth's continued material and technical support. I find myself considering this question honestly, about the difference between a technically achievable goal and a goal that has actually been achieved, or even seriously demonstrated at the necessary scale. A distinction I've returned to throughout this series because I think it matters enormously to how we talk about ambitious future projects. The atomic bomb, difficult as it was, involved solving problems where the underlying physics was already understood with real confidence, and where the engineering challenge, however enormous, was fundamentally a matter of scaling up known processes using dedicated resources and talented people working with real urgency. Mars colonization, in its full self-sufficient sense, involves several categories of problem: closed-loop agriculture at scale, multi-generational radiation safety, permanently reliable life support with no possibility of Earth-based rescue, where we don't yet have confident, demonstrated solutions even at small scale, let alone at the scale an actual growing settlement population would require. I don't think this makes the entire concept a lie in the sense of deliberate deception. I think many of the scientists, engineers, and public figures who discuss Mars colonization genuinely believe these problems are solvable, and I don't have strong grounds to say they're wrong about that belief in principle. What I think is genuinely misleading in the great deal of popular discussion surrounding this topic is the implied timeline and the implied level of technological readiness. Language that sometimes suggests colonization is primarily a matter of political will and funding, arriving imminently once enough resources are committed. when the honest state of the underlying science suggests instead that several of the most fundamental requirements for genuine, safe, multi-generational settlement remain, as of now, unsolved problems at the necessary scale, not simply engineering challenges awaiting sufficient budget. I want to close by returning to something I said in an earlier conversation about interstellar travel because I think it applies here with equal force, adjusted for the very different scale of the problem. Mars colonization does not appear to be forbidden by any fundamental law of physics, the way faster than light travel is. Every individual technical requirement I've described in this conversation, radiation shielding, closed-loop life support, closed-loop agriculture, resilient energy infrastructure, represents a problem that current physics and engineering understanding suggests is solvable in principle, given sufficient time, resources, and sustained institutional commitment. But solvable in principle, and actually solved, demonstrated, and proven reliable at the scale a genuine, thriving, multi-generational human settlement would remain very different things, separated by a gap in demonstrated technological readiness that I think honest physics obligates us to acknowledge clearly. Rather than allowing enthusiasm for an undeniably inspiring goal to obscure just how much fundamental engineering and biological science remains genuinely unfinished before that goal could responsibly, safely become a reality.